Hi everyone, I welcome you all in the next lecture of quantum mechanics. In previous lecture, we have already understood the concept regarding the particle in 1D box, right? So until now, we have studied the particle confined in one-dimensional box where motion was allowed only along the x direction. Now we extend the same idea into two dimension. So in this system, basically what you will see, the particle is free to move, along both x and y direction that you can see here in the screen. X and Y direction inside a rectangular box having length and width of this rectangular box is A and B respectively. But it cannot exist outside because the potential walls are infinitely high. So outside the potential is infinite and inside the potential is zero. Right. So here, the box you can see having along x direction the length is a and along y direction the length is b. And inside this box, that is potential v of xy is zero, and outside the box the potential is infinite. So therefore, the particle is completely confined inside the two-dimensional region. Right. So that is what the boundary condition is, where potential is zero when zero is less than x is less than a, and it is again zero when zero is less than y is less than b, and infinity otherwise. Okay, so from time independent Schrodinger equation, we see that E psi equals to minus h cut square by 2m, and then del 2 psi by del x square plus del 2 psi by del y square plus v of xy into psi. Is that clear? So where you can see that this is in two dimensions. Is that clear? Now we have to solve this Schrodinger equation in order to calculate the wave function, and then further we have to calculate the inner quantized form of energy as well as the the probability density of the finding of the particle in the given region in space. So once we want, so we are interested in solving the Schrodinger equation in the region inside the box where potential is zero. That's why we will have to substitute v equals to zero in the Schrodinger equation. And once you substitute these things, this equation will becomes like that. That is del 2 psi by del x square plus del 2 psi by del y square. That is equals to minus 2 me by h cut square into psi. Is that clear? Okay, great. So now this is second order partial differential equation in two dimension where psi is varying along x and y direction. And in order to solve this partial differential equation, we are going to use the separation of variable technique. That is one of the standard technique to solve partial differential equation, and that will give you the analytical solution for the partial differential equation. Is that clear? So here we are going to assume that capital psi that is equals to a function of x and y, where x will be an explicit function of a small x position in along x direction, and y will be a function of only y along y direction. Is that clear? So, I mean, why this is useful? Already, I have told you that basically transform this method basically transform a difficult partial differential equation into simpler ordinary differential equation that you will see later on. So here, what happens after substituting this psi equals to x and y, you will see this equation will become like that. And again, what happens here? So once we divide and x and y both sides, so this equation will become like that. And let's say this is called as the equation first. So what you can see here that since the first term only depends upon the value of x and the second term only depends upon the value of y, and both of these term must independently equal to a constant, right? So in order to equate these things to equals to constant, I am using here that first term that is a function of x only that is equals to minus of kx square, and second term that is equals to minus of ky square. Is that clear? Great. So now let us first solve the equation along x direction. So this now finally you can see that this equation is a first second order ordinary differential equation, and that is very simple to solve. So you can write this equation in this form, and then finally you will get a solution for x like C1 sine of kx into x plus C2 cos kx into x. right? Something like that. So this is what the solution of this wave equation along x direction. And once we substitute the boundary condition, so boundary condition was at x equals to 0 is 0. And once you substitute the boundary condition, we can calculate the value of C2, and that is equals to 0. So finally, it gives you a eigenfunction along x direction is C1 sine of kx into x. Now, we'll substitute the second boundary condition, that is x equals to a equals to 0. And from here, we can calculate the constant, that is kx into a, that is equals to nx into pi. And from here, we can calculate the value of kx, that is equals to nx into pi by a. It's very simple. Okay, so along x direction, you finally we obtain the eigenfunction, that is equals to c1 sine of nx into pi upon ax. So this eigenfunction is sinusoidal, and that basically depends upon the quantum state along x direction, that is called as the nx. Is that clear? Next, we'll solve the equation along y direction, and that is again another second order ordinary differential equation, and we'll use the same methods to solve these things. And finally, you will get a solution, that is y, that is equals to c3 sine ky into y plus c4 cos ky into y. And again, we can substitute the boundary condition. We have two boundary condition along x and y. And this basically gives you, the eigenfunction along y direction is again sinusoidal, that is c3 sine ky into y. And once we substitute the another boundary condition, that is y at equals to b equals to 0, then this will give you the value of ky, that is equals to nx into pi upon b. Sorry, it should be ny. Ky equals to ny into pi upon b. Sorry for my mistake, right? So basically, it will give you the, sorry, again here it should be ny into pi divided by b into y. So it will give you basically y. Y will be equals to c3 sine ny into pi upon b into y. Okay, so that's great. So finally, we can write the complete, solution of wave function, that is psi, that is x into y, and we have already calculated the value of x and y. And once you multiply these things, this will give you the value of c1, c3 sine nx into pi upon a into x, and into sine ny into pi upon b into y, where nx and ny is the quantum state along x and y direction respectively. Now, next thing is that we have to calculate this constant, that is C1 and C3, that you can see in the wave equation. And previously, I have already discussed how we can calculate this constant using the normalization or orthogonality of wave function. So once we use the orthogonality, that basically tells you that double integral of minus infinity to infinity uh, mod of psi squared dx dy equals to 1, because the domain of x will range from minus infinity to infinity, and for y it is same. And once we perform this integration along x and y direction, because here your domain is x equals to 0 to a and y equals to 0 to b, because length along x and y direction of the rectangular box is a and b. And finally, doing the square, performing the square, that will give you sine square and x by a, and sine square and y pi y by b dx dy. And you have to calculate this integration, right? So again, you will use some trigonometric identities like 2 sine square theta equals to 1 minus cos 2 theta, something like that. And this will get transformed in this particular form. And once you do this, trigonometric identity expansion, and then you have to do this integration. And after this integration, you can substitute the limit from 0 to a for x and from 0 to b for y. And after doing these things, we are getting the value of c1 c3 square, that is equals to 4 upon ab. And finally, you can calculate the value of constant c1 and c3, that will give you, that is root 4 by ab. Okay. Great. And finally, once we substitute this value of constant in the equation, in the wave equation, you can finally calculate the final wave function, which is a function of x and y, as well as a function of number of quantized state along x and y direction, that is nx and ny. And also it basically depends upon the value of a and b length along x and y direction respectively. Okay, so this, and after that we can also write the final equation in that will include the time varying part as well. And already I've discussed these things, how we can calculate the time varying part of the wave equation. And finally, this is the final wave equation that will be a function of x, y, and t respectively. Is that clear? And the plot I'll show you later on. First, I'll discuss here the probability density, and then we'll show you the plot today. Okay, so what we have seen there, so where we have seen that nx and ny is the quantized state, and finally, once we substitute the value of kx and ky in the above equation, we will be getting that is minus 2 me by h cut square, and from here we can calculate the quantized energy for particle that is confined in 2 dimensions. Right. So notice something that is very important. So energy now depends upon, two quantum numbers, that is nx and ny. Right. So earlier, when it was a particle in 1D box, it was only a function of nx, that is one quantum number. But here, part energy is the function of two quantum number, nx and ny. And this is one of the major difference, from one-dimensional box. Is that clear? And then we can calculate the probability density because we know the wave function. And in order to calculate the probability density, we have to calculate the mod of, probability wave function square. And from here, you can either write in terms of psi of xy, or you can also write in terms of psi of nx and ny. Is that clear? So this equation basically tells us where the particle is most likely to be, found inside the two-dimensional box. Is that clear? And after that, we can say that the quantum confinement in a multiple dimension produces complex standing wave probability pattern, because earlier it was only a function of sign, but here you can see there are two sine wave that is getting multiplied, and then that is becoming very complex, right? So what we have seen here, that two-dimensional particle in a box forms the foundation for understanding the quantum wells, nanostructure, quantum dots. That is also very much useful in semiconductor confinement and modern nanotechnology. All of these things are the application of the quantum particle in 2D box. So let's see how we can, because plotting this kind of mathematical function is very difficult, because this is very complex mathematical function and it's not very easy. So there are software that is available. I'll show you that software, that from where you can see how wave function is varying along nx and ny, or if you're varying x and y, and also how probability density is varying. So let's see how it varies. So this one is the plot that you can see here. Is that clear? And here, basically, what you see, if I'll change the value of nx and ny, you can see this plot will vary. So this first plot is for wave function, and second plot that is for the probability density. So let's say nx is 1 and ny is 1, then it looks like that. If I'll do nx is 2, then you see this basically it got changed. So now wave function is kind of complete sinusoidal thing, something like that. And again, probability density is looking like that. Okay. So this is how this looks like. Okay. So, I mean, it will, as we have we have already seen that it is basically going to depend upon the value of nx and y as well as x and y. So here you can see that this is a maxima along y direction, this is minima, and the probability density will always be positive. That's why it looks like that. Let's try to change ny. So if I'll do ny equals to 2, see how it will be like that. So along y direction also you can see it is coming like that. That clear? So basically what is happening, you can see that four peaks are there, and where the probability density or probability of finding of the particle is maximum. So here you can see that probability density at this point, at this point, at this point will be maximum, and there is valley where the probability density of particle finding is 0. And again here you can see that for the wave function, here the wave function is making maximum along y, and here it is going minima along y, something. So let's try to send nx along 3. So if I'll do 3, then what will happen? So you can see here the wave function is also changing, and obviously probability density is also changing, something like that. So it looks very interesting, and based on this you can find out the probability density of finding of the particle in the given region in a space, and the particle in 2D box, where x equals to a is the length along x direction, and x equals to b is the length along y direction. Let's say I'll do n equals to ny equals to 3. So now again you can see it got changed completely. So it is having some deeper meaning as well, right? Because you can see that if you are changing the quantum state along a x and y direction, then probability density of finding the particle in X and Y direction is changing. And this looks very interesting. Okay. So, I mean, this ends the lecture for, particle in 2D box today. So I'll stop the lecture here only. In next lecture, I'll start discussion about, hydrogen atom, and then we'll move towards the quantum tunneling. That is also very important application of the quantum mechanics. We will see lots of, interesting phenomena that happen, and I'll also tell you the historical development of quantum tunneling, and why quantum tunneling is very important in, present days, quantum computing. Right. Thank you. See you in the next lecture.